Hello and welcome to the first lesson for Math 252 on the asynchronous Thanksgiving break week. So previously we learned about parametric equations, so now we're going to talk about the calculus of them. So let's start out with the parametric equations. X is equal to 5t minus 3, y is equal to 4t plus 7. Okay, go ahead, take a moment, pause the video, and attempt to solve the problems on this page, and then we will talk about them. So, calculating dx dt, we have the derivative of 5t minus 3 with respect to t. That gives us 5. dy dt by a similar process gives us 4. As was talked about earlier, when it comes to eliminating the parameter t, two main avenues. One is to solve for t, the other is trig identities. Given that neither one of these functions contains any trig, we're going to solve for t in one of them and plug into the other ones. Just by the fact that x is written first, I chose to solve for t in the x equation, which you can do by adding 3 and then dividing by 5. You could also do this by solving for t in the y equation, and you would achieve a similar result. If we solve for t in the x equation, we would then plug this in instead of t in the y equation and simplify, which gives us 4/5 x plus 47 over 5. Now the second part of this question asks us, what is dy dx? Well, dy dx would be the derivative of this equation right here. So the derivative of this equation would be 4/5, as derivative of x is 1, and the derivative of a number is 0. So it's 4/5 times 1, which is just 4/5. Now, if you thought about this question, well, look at dy dt and dx dt. Now, think about what happens if we have dy dt over dx dt. Well, as a general rule with fractions, we can multiply by the same thing on the bottom and the top. This would leave us with dy dx. It is worth noting that with differentials, you need to be careful about applying common operations, because differentials such as dy, dx, and dt do not obey all those common laws, and there are some times where common math with differentials is incorrect. However, in this case, it is a way of remembering it, and yes, for parametric equations, we can take the derivative of the function of y in terms of t and the derivative of the function of x in terms of t, write them as a quotient, and that will give us the derivative. So this first part is the definition that we just talked about restated, and that is for a pair of parametric equations, we can find the derivative of y with respect to x by taking the derivative of y with respect to t and dividing it by the derivative of x with respect to t. Now, let's go ahead and apply that to a specific situation where we have x is equal to 7t and y is equal to 40 minus 5t squared. You may recognize this as being similar to what we went over in class, as this also is a representation, albeit more rounded than the one we did in class, of an object launched at an angle with no air resistance. So for the first part, we are asked to calculate the derivative of these parametric equations. Doing so, first of all, we have dx dt is equal to 7, and dy dt is equal to 40 minus 10t. Using the rule above, we get dy dx is equal to 40 minus 10t over 7. Now, for the next part of this, what happens at t equals 4? Immediately, let's look at the derivative. If we look at the derivative as for t equals 4, the top becomes 40 minus 40, which is 0. The bottom is just 7, so 0 divided by 7 is 0. So this may raise some memories from Calculus 1. Because in Calculus 1, or Calculus derivatives as it is called in the catalog, we specifically talked about when the derivative was 0 as being commonly indicative of a local or absolute maximum or minimum. Well, now, with regard to this graph, it ends up being a maximum. If we go ahead and we eliminate the parameter by solving for t on the x equation, and then inserting that into the y equation, we end up with this parabolic graph here, 40 over 7x minus 5 over 49x squared. This graph, if plotted on a graphing calculator, results in a parabola. Specifically, this graph has a maximum value at x equals 28, y equals 80. Noting that x is equal to 7t and 28 divided by 7 is 4, this maximum value happens at t equals 4. So this value where the derivative is 0 indeed is an absolute maximum value for this graph. And as such, we have a similar rule to what we had with functions of y versus x that were non-parametric, and that is, if the derivative is 0 or undefined, we will have a critical point for a function defined parametrically. So, now, let's calculate some derivatives of parametric equations. So let's start out with this first one, where we have x is equal to 3t minus 5 and y is equal to t squared minus 7t. So the derivative, dy over dx, will be equal. On the top, we will have the derivative of y with respect to t, which is 2t minus 7. And on the bottom, we will have the derivative of x with respect to t, which is just 3, as the derivative of negative 5 is 0. The second part of the question of the prompt for this series of problems asks, identify any critical points. So critical points are where either the derivative is 0 or does not exist. In this case, because the denominator is 3, we will never be dividing by 0. And so the derivative will always exist given that the top, 2t minus 7, is defined for any value of t. So that means to identify critical points, all we need to do is set the numerator, what is on top, equal to 0. We can then solve this equation by adding 7 to each side and dividing by 2 to get a critical point that occurs when t is equal to 3.5. It is worth noting that on a graph, to find the exact point at which this critical point occurs, we would plug 3.5 in for t on both x and y. However, since this is merely an introduction to the calculus of parametric equations, for the sake of time, we will skip this step for now. We next move on to x is equal to the sine of, 5 times the sine of t, and y is equal to 5 times the cosine of t. For this, our derivative will involve taking dy dt, so the derivative of 5 cosine of t is negative 5 sine of t, over dx dt, the derivative of 5 sine of t is 5 cosine of t. For our critical points, the derivative will be 0 when the numerator is 0, and the derivative will be undefined when the denominator is 0. So for our critical points, we will set the numerator equal to 0 and solve, and we will set the denominator equal to 0 and solve. From trigonometry, sine is 0 when t is equal to 0, pi, and 2 pi if we limit ourselves to the first rotation. Also, cosine is 0 when t is equal to pi over 2 or 3 pi over 2, again if we limit ourselves to the first rotation. And from that, we have identified our critical points. The third example is omitted here for time. It will be shown on the notes posted on Canvas. We discussed recently in talking about Euler's method the use of tangent lines. Hopefully you remember the point-slope form of a line from that discussion or from earlier. If not, I will provide it, as we will be using that to find the equation of tangent lines of functions defined parametrically. So, the point-slope form of the equation for a line is y is equal to m times x minus x1 plus y1. Now, think to yourself, how can we calculate each of those from the information given above, where we have x is equal to t squared minus 8t, y is equal to t cubed minus 12t, and t equals 3. So the first part of this is m, the slope, is the derivative at the indicated point, or in this case, t value. So we then need to calculate the derivative and plug in 3 for t. Calculating the derivative, we get 3t squared minus 12 over 2t minus 8. To find the slope of the tangent line, we take our value of t equals 3, and we substitute that for t to find m, which calculating gives us 15 over negative 2, which a positive divided by negative is a negative, so we may write that as negative 15 over 2. Now, think about how we could calculate x1 and y1. So, to find x1 and y1, we plug our indicated value of t into, first of all, our equation for x to find the x value at that time, which in this case gives us negative 15 for the x value, which replaces x1 in our point-slope form of the line. Then we can plug t equals 3 into the y equation to find our indicated value of y, which goes in for y1. This now gives us the equation for a tangent line. This can be further simplified, however, again, for the reason of time and for the reason of you have done this before in other courses, we choose to leave it in this form and not simplify it. The last concept that we will go over in this video, as what I am considering to be part 1 of calculus of parametric equations, is the derivatives of parametric equations. So for that, we're going to talk about calculating second derivatives. Higher order derivatives are possible for parametric equations. However, beyond a second order derivative, there becomes less use, as for physical applications, the second derivative represents acceleration. Beyond that, further derivatives are seldom used, or at least are not used anywhere near as regularly. So, For parametric equations, there is some similarity to the past. In Calculus 1, Calculus of Derivatives, to calculate the second derivative of a function, you took the derivative of the first derivative. Now, we're going to do that. However, we note that when we're finding the second derivative with respect to x, our derivative is defined in terms of t. So taking another derivative in terms of t is insufficient, as, again, our variables are different. So for parametric equations, in addition to taking another derivative with respect to t, we also have to divide that by the derivative of x with respect to t. And from that, we get our second derivative. So let's apply that to a function. Earlier we found a first derivative for this function. For that reason, I am just going to choose to show the equation for the first derivative as is the same process we did earlier. So once our first derivative is found, we are now going to take a derivative of that with respect to t. Unfortunately for us, as commonly happens, this becomes a quotient rule, which, yes, is a very annoying form of derivative. Applying the quotient rule to that derivative gives us, by the good old rule of high d low minus low d high over low squared, 3t squared minus 5 as low times 2 minus 2t, which is high, times 6t, which is the derivative of low, over 3t squared minus 5 squared. We will then have to take this and divide by dx dt. Using this rule and dividing by dx dt gives that. We can further simplify this, noting that if we're dividing by 3t squared minus 5, that would go in the denominator on what we are dividing. This then gives us, along with distributing in the numerator, the result 6t squared minus 10 minus 12t squared. We can further simplify that, noting that 6t squared minus 12t squared is negative 6t squared, and that is equal to 2 times 3t squared minus 5. Applying that and canceling gives us a final result of negative 2 over parentheses 3t squared minus 5 parentheses squared. And this is our final result for the second derivative of this function. Thank you again for watching this video. For those of you watching this before Thanksgiving, I want to wish you a happy Thanksgiving. For those of you watching this video afterwards, enjoy the remainder of your break, and I will see you in class soon. Bye.